You have probably used or saw someone else using a digital multimeter to measure AC voltage, where it gives a constant value. But we all know that AC voltage is sinusoidal and constantly changing over time. So, where does this value come from, and what is the intuition behind it? To understand the logic behind it, let's start with the basics. Something simple like a DC circuit. In this DC circuit, we have a DC voltage source connected to a resistor through a switch. And when we say DC, we imply that its polarity does not change over time. In addition to that, in our example, we will also assume that its value is constant over time. So, once the switch is closed, we expect the current to start flowing instantly. The value of that current is given by Ohm's law as V divided by R. Since V and R are both constant in our example, the current is going to be constant too. However, in real life applications, knowing the current is just one part. What we also care about is the cost of running the circuit. In other words, how much energy it uses over time. To find the energy, we need to be able to measure two things: power and time. In any circuit, however, what dictates the power consumed or generated by any element in that circuit are the voltage across it and the current flowing through it. Mathematically, this is given as P equals to V times I. If you are wondering whether that makes sense, just recall that voltage is energy per unit charge, current is charge per unit time. Multiplying them together, we get energy per unit time, which is power. Since V and I are both constant, power is constant too, as expected. Note that we can also find power using other equivalent formulas. By substituting Ohm's law in the power equation, we can have P equals to V squared over R, or P equals to I squared times R, all of which agree with the main power equation, which is V times I. It's good to keep these in mind as we will need them later. Now, let's step into the real business, AC circuits. Let's go back to the same circuit and replace the DC source with an AC voltage source. In AC power systems, the voltage is sinusoidal. It has a peak value, which is simply the maximum and minimum values that the voltage keeps bouncing in between. Also, it has an angular frequency, which is given by 2 pi over t, where t is the periodic time. In most of the world and where I live, t is 20 milliseconds, which corresponds to 50 Hz. In the US, for example, the frequency is 60 Hz, meaning the period is shorter. Lastly, the voltage wave has a phase shift that represents the starting point at which we start measuring. If it happens that we start measuring at zero crossing point, the phase shift is going to be zero. If it happens to be at the peak, the phase shift is going to be pi over 2 or 90 degrees, and so on. Let's assume for now that we start at the zero crossing point, so no phase shift. So what does this mean for power? Well, since voltage is sinusoidal and the resistor is constant, the current is going to follow the voltage with the same frequency and phase shift, but with different peak, which is in our case is going to be V peak over R. Since power is V times I, the power now is variable unlike in DC circuits. From the DC analysis, we found that the power can be represented as V squared over R. We will use this formula to represent the power from now on. This power is called the instantaneous power, as it gives the power at a certain instant. At the zero crossing, both voltage and current are zero, so power is zero. At the peak, both are at maximum, so power peaks too. The power is always positive, because a negative voltage multiplied by a negative current is still positive. Now, let's have the two circuits side by side and ask a critical question. What is the DC voltage that will yield the same energy as an AC voltage within one periodic cycle? The answer to this question is the underlying intuition behind RMS values, as we'll see soon. There is also another keyword in this question, which is going to guide us to where we should start in order to find an answer. That word is energy, which renders the problem into an energy balance problem. So, to work out the energy balance problem, we need to find the energy yielded in both circuits. In general, energy is given as the integral of power over time. In our case, we will fix the time for both circuits to be one periodic cycle, which is denoted as T. To work out the energy in the DC circuit first, we will replace the power with V squared over R. The power is constant, as we discussed earlier, so we can take it out of the integral. The integral of 1 over 1 periodic cycle simply becomes T. Finally, we will just call the voltage in this formula V effective from now on. Now, let's do the same for the AC circuit, replacing the power with V squared over R as we did in the DC case. However, the voltage here is not constant, so only R can be taken out of the integral. Now, we have the necessary recipe for our energy balance problem. Equating both energy quantities, we can cancel out R from both sides and then divide by T. The right-hand side of the equation is nothing but the formula for the average value of a function, which is given by integrating the function over a certain interval of the independent variable, in our case, time, and then dividing the result by the length of that interval, which is in our case, the periodic time, T. Then, taking the square root of both sides, we end up with the effective voltage being equal to the square root of the average of the squared voltages over one periodic cycle. Hence the name RMS, root mean square, the square root of the mean of the squared voltages over one periodic cycle. Now, let's take the final step and evaluate the actual value of that effective or RMS voltage. To do that, we will replace the voltage by its sinusoidal function, taking the peak voltage squared outside the integral and then performing the integration over one cycle. We end up with the fact that the RMS value of a pure sinusoidal voltage is given by the peak value divided by the square root of 2. Hence, anytime you see the RMS value of an AC output voltage, it actually means the peak value divided by the square root of 2. This value is derived to be analogous to a constant DC voltage that yields the same energy if applied to the same load over one periodic cycle. You might have also noticed that I am frequently stressing the one cycle time frame. This is because if it is of interest to find the RMS value over less than a periodic time, then the RMS value will be different and dependent on the fraction of that cycle, as we can see here. So that's it. Hopefully by now you have developed a solid intuition for how we arrived at RMS values. Thanks for watching.